live and good evening. Welcome to Northwest Nuclear Laboratories on the 14th of August. Can't believe it, the year is slipping by so very fast. A lot of amazing things have developed. How many saw the announcement for the Microsoft Duo?
I didn't.
Okay.
What is that?
It is a cross between a tablet and a cell phone, and it's called the foldable. So this thing folds up like a little paperback book, and you can stick it in your back pocket and whatever. But if you're going someplace and you're out at a diner, you can just pop this thing open, and there's no seam. It's a very tight little two screens together, and all of a sudden you have what appears to be a little tablet that you can run the full Microsoft Office, and yet you're still hooked up through your telephone company. So you can make phone calls and all that happy stuff. It's quite the little gadget. 1,300 bucks. So, and that's where they start. But
How much memory does it come with?
I don't know. I didn't participate in the prototype. I have servers to run, and so I have enough demand for horsepower that I can't take something that's lightweight around. So my Surface Book is about as small as I can go. Okay, so can I have a show of hands regarding anybody that actually saw that I sent them an email today with tables? Ooh, Christina. Great. Cool. Okay, so what's going on is we're going to do a postmortem tonight and kind of try to figure out where we are. I'm going to reference the tables. It's very apparent, first of all, looking at the tables, that we changed the methodology that we were using to collect the data from going around the reactor at one voltage to going to one location and then stepping through all the voltages. So these two data sets were actually captured with these two different methodologies, and I have to pull the data out of different locations in order to get apples to apples. There were also problems on the data sheet for 70,000 volts. And I tried to correct them, but when I went and looked at the normalized picture, 70 is definitely got some issues. So I retreated to the 60,000 volt session, and I used the 60,000 volt session to populate a normalized east-west and a normalized north-south. And they seemed, for the most part, to line up fairly well. And of course, what I'm looking for when I stick in the numbers, because we are different distances from the center of the reactor vessel, is I'm looking for the same computed isotropic output. In other words, what's the total isotropic output of the reactor? And so we'll take a look at normalized east-west. Um, in the north-south configuration, I have 117 and 133. That isn't that far apart, but that isn't where the reaction is taking place. That's not where the plasma is. So I expect some deviation there. But when I look at the east-west, they come out in the 150K, and they're close enough. I think within 2K. And so one was 30,000, one was 28,000. You can clearly see that those align very nicely. And then I come down to the normalized north-south, and I stick in the numbers. And in the east-west, I saw 77 versus 82, close enough. And 177 versus 183, again, close enough. So the hot sides north and south, and that caught me by surprise because, yeah, they're close enough, they're normalizing nicely, and so I know that the data is valid. If I tucked in one of those numbers and it bounced clear out to na-na land, I would have known there was something wrong. And in fact, I did that with the 70K. I stuck 70K numbers in here, and they don't line up, and they don't add up to the same isotropic. So they're not valid. But looking at this, the east-west on the hot side seem to have an isotropic value of about 155K, and the north-south had 170 and 183. And when I saw those numbers getting collected last week, I said to myself, gosh, that's supposedly the cold side. And indeed, in terms of temperature, it was. But they aren't lining up. I mean, it just doesn't make sense why they would be the same, and there's this difference in design and so on. And that's when another rabbit hole appeared before me that I'm going to discuss tonight. When I went to set up the experiments for last week, that's the north-south configuration, on Friday, about the middle of the day, it was still an east-west scenario. And so I said to myself, we've got to open up the reactor, twist the thing 90 degrees, put it all back together again, and then we need to dry it out because we're going to pick up some moisture. We're going to probably get some finger oils in there. Outgassing is going to be a problem, and that's going to retard neutron production artificially. So I'll pull the con flat, do the twist, put it back together again, and then I'll bring it up at a low voltage and just let it cook for a couple hours to get all of the impurities out of it and all, degassing and whatever else. Well, something we learned a couple of years ago, and I had forgotten about it, is that there is a mode that we can get into with this IEC reactor that I will simply call front loading. And what I mean by front loading is if we bring up the reactor, turn the high voltage down and turn the gas way up, and balance it just at the edge of neutron production. So you're getting a few neutrons, but not a lot. And you're running a whole lot of gas into this thing. What happens is you start building up a film of deuterium on the surfaces in the reactor. It actually embeds these deuterium ions in the plates so that you have this substantial number of ions in the target field, and when you crank it up to production levels, you're immediately seeing very high levels of radiation coming out, but it's for a relatively short period of time while you're burning off this excess embedded neutron that you have been front loading the reactor with. And I went, wait a minute, that's a variable that can trip us up. It could very easily impact readings. It could very easily be causing a false delta here. So tonight what we're going to do is I'm going to go ahead and go into the reactor room, and we're going to start by simply bringing up the reactor. I haven't run it at all today, so there's been no activity at all. And I'm going to bring it up, and I'm going to go to the south position exclusively, and we'll grab a couple 3 numbers off the south position at a given temperature, and then we're going to set that thing up to start front loading. And we'll let it front load for a half an hour. And then we'll come back at the end of that time and jump up to the same power level that we were running earlier and see if we're getting the same number. And if we aren't, then how big is the delta? And the intent here is to get a handle on, get our head around how big a delta are we dealing with, and is this something that could significantly affect the outcome of this experiment? If so, then I may have already tripped us up last week. So that's what we're going to do. The reactor is warmed up, so we can go right to capturing our data. Oh, probably would help if I turned on the head cam.
Yes.
Okay, so let's do that. Okay, do you have the head cam?
Yes.
Okay. Oh, that sounds so lovely. Okay. Okay. I'm going to go ahead and open up the gas. We're going to start up with a substantial amount. Does somebody have a sheet that they can use to record some data?
Yeah, I can print out another data collection sheet.
Okay, why don't you go ahead and do that before I get started?
Do you want multiple people or just her?
I'd love to have multiple people. I had one sheet for last week and it had errors. So that's why the 70,000, I couldn't go anywhere with it because I had some bad data. And I don't fault the person that was capturing the data because that's just being human. That's why we have multiple people collecting it. But if you collected data for last week and didn't send it to me, would you please send it to me, because then I can correct those sheets, because I do want to take a look at the 70,000.
Sure.
Appreciate that. Are you ready to go, Christina? Not yet. Can someone tell me if that camera is covering the nuke? The little meter, the box?
You can see the meter.
You can see the meter. Good.
What did you say the laser orientation was?
The current orientation is north-south. And we're actually just going to capture a couple of numbers just to get a feel for what's going on. I don't want to do a whole series. Because if this is happening, then it's going to be real obvious real fast. Let me know when you're ready to go, Christina.
Oh yeah, I'm ready.
You ready? Okay. All righty. So I'm going to jump up and get a couple of high-level numbers on the south right away. Okay, we're up and flying. The temperature is 77, 76 on the front and rear, which is our north and south. They're both reading 76 right now. having a problem here. A little bounce there. Okay, I'm sort of at 70,000. I'm going to count now. Now I'm going to be riding the voltage really hard here because it wants to run away from me. Tell me when it's done counting, okay?
We can't see the counter right now. It's at your chair, desk.
Oh,
No, I see the
I
count.
see the count. I see the counter.
Oh, I think. Oh, my screen swapped.
The counter stopped.
okay, grab that number. Let me know when you got it.
I had it.
Okay, I'm going down to 60. And we'll take a
Christina,
snap.
is there another number you need, like the D2 or something?
Not for this particular exercise. Okay, I'm at 60 and
Okay.
restarting. I will give you the D2 for this. It's 2.5.
Is this the south conflat, just to make sure?
I'm sorry, I couldn't hear you.
Which conflat location is it again?
This is the south. So
Thank you.
it's the one that's directly facing this direction. So
What temperature did we have?
so this face right here towards the south.
The counter stopped.
Okay, you got them both?
Yep.
Okay. Now what I'm going to do next is we're going to bring up a whole lot of gas. I'm going to try to park this thing right down around 30,000. We're at 3.9 for D2. And we're getting some spitting some stuff, but not a lot. Okay. Now, we've started front loading, and I will, in the meantime here, take you on an adventure. Okay? For those of you who remember, this is our furnace room. Okay? It's no longer the furnace room. It is now called the pump house. Okay? What you're seeing here is the manifold and something we call the UVC oven. I'm going to go ahead and fire up the UVC oven. And you can see that little blue light there. Correct?
Yep.
Okay. So inside this thing, that's a 4-inch 304 stainless steel tube, 1/8 of an inch thick. And inside of it are two 3-foot germicidal lamps, 30 watts apiece. And they're creating a furnace, if you will, of UVC radiation in the neighborhood of about 15 millijoules. So all through this section of pipe, at any point, if you were to put a detector in that pipe, you would register 15 millijoules, which is actually quite a bit of UVC energy. Okay. Okay, the pump is on, and the airflow is massive. You kind of see the effect on my lab coat. Now this particular manifold has 1, 2, 3, 4 exits. And that's going to go out to 4 main arteries that feed all the labs. And a lot of air there. Now, in order to give you an idea of what this is like, I'm going to have to take my head cam off for a minute and try to do something tricky here. I'm not going to be able to hear you right now. I've had to set my headphones down. I'm going to hang you on the doorway here for a second. So here I am in the hood. I know this sounds pretty weird. Yeah, okay, so it is getting me correctly. And the system is supplying my air through this flexible tube. Comes around, connects into my helmet. Actually, there's quite a bit of cold air here. And you can see how quickly my condensation from my breath vanishes off of this mask. And that's because the air is chilled and dry. Ordinarily, it won't be pulling on me because I'll have a clip on the airline and I can go from location to location and click into any pipe and get an air supply. So that's how it works. And that's how easy it is to take off. Woohoo! If I got this sideways, wait a minute now. Okay, no, we got it straight up. Okay, so I'm going to get back into my headset. Okay, I'm back online. I can hear and see again. Woohoo! Any questions? Nah. It's been a lot of fun constructing this thing, and there's quite a bit of science that's going on in terms of calculating the amount of radiation. But one thing you should know about COVID, of all the different organisms that I've looked at and interacted with, the COVID virus, coronavirus, is the most susceptible to UVC that I've ever seen. It only takes 611 microwatt seconds to kill it. So that's 0.000611 microwatt seconds. Conversely, flu and staph infections, those kinds of things, all take 79,000 or 8,000 microwatt seconds to kill. And so We're talking less than a tenth of the amount of energy that it takes to kill corona. And so here's this really dangerous virus, but it has a weak spot. And that weak spot is UV radiation. And that's where we need to leverage what we understand about radiation and technology to create a beachhead around the spread of coronavirus using that weakness. Dave, was there anything on that? Could you see fairly well what was going on with?
Yes,
Okay,
very well.
all right, good. I turned on that pump to give you an idea. We're going to be moving about 125 cubic feet of air per minute through this pipe. And we only need 15 cubic feet per minute to service everybody and a few guest speakers and some looky-loos. So up to 16 hoods can be attached, and we'll still only burn 15 to 16 cubic feet of air a minute. The pump delivers 1,500 cubic feet a minute. So all of the excess air we can use for cooling, we can use for circulation, use it for other things to make our ride more comfortable, so we don't get hot and sweaty in these things. And that's the thing that excites me, is that you're not climbing into, those of us who've actually put on a full body suit, radiation suit, with gas masks and everything, you really get hot and sticky in there in a short amount of time. I mean, after an hour, you're just drenched. This won't do that because you're getting an airflow in there constantly, and it's pushing out all the moisture. So moisture can't even form on your visor. There are some questions, some safety issues, and some training, like what happens if you need to sneeze with this thing on? If you take it off, theoretically you're exposing yourself and everybody else to coronavirus, so you can't do that. If you sneeze directly into your face mask, that's going to look nasty. So, some of these experiences, you're just going to have to go to the restroom, and it's a paper towel event, and there you have a pipe you can click into, and you can take your hood off, and you can service the situation. But people don't realize, hey, that's what happens to astronauts all the time. They're facing all these same challenges. If we go to Mars, same challenges. And what's cool about that is those of you who participate in the pilot will actually be getting some significant astronaut training in the process. You're going to face a lot of the same kinds of limitations and encumbrances that the astronauts faced in the early part of the space program. And certainly you'd be facing these same things if you landed on a planet that had an atmosphere, but the atmosphere was poisonous and you can't breathe it. So there are a couple of planets like that. We would not want to land on Venus for any reason because the temperature at the surface of Venus, night and day, is totally intolerable. It's like 800-900 degrees. But in planets or environments that have some kind of atmospheric pressure, it may not be necessary to wear a full spacesuit, but you're going to have to wear some kind of breathing apparatus in order to accommodate. And then the question also arises on planets where there may be microbial life. Until it's established what that microbial life is, you certainly don't want to be exposed to it. So these same kinds of precautions would be used. It'll be interesting to see now that the space program's back on the road, how far we get with it. Okay. We'll go back now and now that we've run the thing for a little while, and try to recapture our numbers.
Did anybody happen to record the time that we stopped recording numbers?
That's a no.
I believe so.
Okay, we are at 79, 78 as opposed to what, 76. So it's only been a couple of degrees, but we burned some time front loading. And now I'm going to whiz back up to those 2 data points. Okay. Can you see the PC?
Yes.
Yep.
Okay. All right, I'm heading for 70,000 volts. $70,000, and we're going to start counting neutrons. Give me a heads up when we done counting. The isotropic output here shows over 1 million neutrons per second. That's amazing.
It's done telling.
Okay. So heading up to, we're heading down to 60,000. Guys got it?
Yep.
Good, good. All right, 60,000 and we're pushing the button. We're at 2.9 at 60,000. That I believe is a different number.
It is. Last time we were at 2.5.
That's substantial.
Why do you think that is?
We're going to go back up to 70 and grab that other number. But let's get the 60 number first.
Wait, do you mean going? Do you want the D2 level for 70, the last one we did?
Yeah.
I got it at 2.7.
Ooh, you're good. Okay. So we got 60 and 70 D2 and 60 and 70 D2 this time? Or no, I need to run up and get 70. All right, so have we got the neutrons from this time?
Yep.
Okay, so I'm going to run back up and we'll get 70. So it looks like it was 2.7. Okay, power down. Okay, Christina, what do you got between before and after?
For the neutrons,
Yeah, tell me a story.
so at 70 kV, the first time we had almost 43,000, and then the second time it was like 56,000.
Wow.
Yep.
And then for 60 kV, it was 33,000, and then 37,000.
Okay, so we do have a front loading factor. Oh boy.
Big one.
Well, what that tells us is we have another variable that's as impactful as temperature. And we're going to have to stop and think about what that's telling us and what we need to do to stabilize it. We're going to go to